The next topic that we have is the analysis of fluid flow. Now, before going through some lengthy derivations, let me give you a motivation to study these derivations. Okay, so let's say you are given this problem. So this problem I have taken from Fox and McDonald's Introduction to Fluid Mechanics. So the problem states that water from a stationary nozzle strikes a flat plate as shown. So there is a nozzle which is of this shape, and the water, so there is this water which is flowing inside this pipe and comes out from this stationary nozzle like this. Let's say the stream looks like this. Okay, and this is a plate on which this is incidenting upon. Now the question states that the water leaves the nozzle at some velocity. So this is some velocity of the water. Okay, the nozzle area is given to you. The speed of the water that is leaving from the nozzle is given to you. Assuming the water is directed normal to the plate, so let's say this incident angle is 0 degrees with respect to the area vector of this plate and flows along the plate, so goes like this. Determine the horizontal force you need to resist to hold it in place. So let's say, so the question asks you that if you want to hold this plate stationary, what is the amount of horizontal force? Let's say that force value, magnitude of that force is Rx. So what is the magnitude of that Rx that you need to apply so that this plate remains stationary? Okay, so let's say you are given a problem like this. Now how would you solve this problem? So currently we don't have the knowledge to solve this problem. Okay, so we'll derive, let me just write it from here. So we'll derive Reynolds transport theorem and we'll derive some important equations from which we will derive some important equations that will lead us to answer these kind of problems. Okay, all right, so if the motivation is clear to you, let's study analysis of fluid flow. So let's say we have a fluid flow like this. Okay, and we have injected some tracer particles inside this fluid. Now using these tracer particles, let's say I want to track the motion of certain infinitesimal fluid elements. Let's say this fluid element or this fluid parcel is 1, this fluid parcel is 2, this fluid parcel is 3, this fluid parcel is 4. Okay, all right, and I want to track with time how these fluid parcels move. Okay, so let's say this corresponds to the initial position of fluid parcels, and let's say after some time, after time dt, let's say they have moved because of the flow, they have moved like this. Okay, so it's not necessary that the distance between among these fluid elements should remain the same. because fluid flow can be like anything, and let's say the distance among them has, the average distance among them has increased. So let's say this is 1, this is, so let's say this, I think so these are 4, these should be 4. Okay, so let's say this is the 4th parcel, this is the 2nd, and this is the 3rd fluid parcel. Okay, so this corresponds to the position of fluid parcels after time dt. Okay, let me draw 3 like this. Now if let's say this is a boundary consisting these fluid parcels, and similarly this would be the boundary consisting these fluid parcels, then this boundary across which the mass does not change, this is called control mass. So control mass is nothing but a boundary across which the mass, the contained mass, does not change. Okay, so can you think of an example, some examples where you have studied the problems using the concept of control mass? Think about it. You've already done some problems. So in thermodynamics we use this concept of control mass. So in thermodynamics you must have studied problems where you had a cylinder and a piston attached to it. Okay, and there was these gas molecules which were inside the cylinder. So this boundary there was the control mass. Since even if, so this is a piston, so even if this piston is pushed inside, let's say like this, then let's say the gas molecules look like this, the density would increase, but, and this is your control mass. So in both these cases what's happening is the mass of the gas molecules is not changing, right? So that's why for such problems this was our control mass. Okay, so these kind of systems are also called closed systems. Okay, now let's say in fluid mechanics, when you are dealing with flow through a pipe, is it a closed system? Not, because the mass of the fluid elements does not remain constant. It could be the case that for certain time the mass is more and for some other time the mass is less, right? So that's why in fluid mechanics, and also the same molecules are not there inside the pipe all the time, right? So that's why these kind of systems are called open systems, right? So in fluid mechanics, instead of defining control mass, what we define is control volume. So let's say for this problem of flow through pipe, I'll define a control volume like this. Okay, so this control volume is nothing but a boundary across which mass, momentum or energy can flow or pass. Okay, so as we can see over here, the fluid molecules can move inside this fluid element and can also exit from this control volume, right? So we do not limit our study on particular fluid molecules. Instead, we are interested in studying certain problems where we fix the volume. For example, here we were interested in knowing various properties like the velocity of the fluid inside this pipe, etc. So we define the control volume to study about those properties. Okay, so now as we can see here, this is not very different from the Eulerian description. Okay, right, and this control mass is not very different from the Lagrangian description. Now, like we did in the Eulerian, we did in the Eulerian and Lagrangian description, we found an expression which relates the Lagrangian description with the Eulerian description. You remember? So we derived d by dt of some quantity q equal to del q by del t plus v dot grad of that quantity q. So similarly, we also want to derive a relationship between the properties that I measure from control volume and how are they related with the properties from the control mass. Okay, so we use Reynolds transport theorem to find that relationship. So Reynolds transport theorem allows us to relate rate of change of some quantity in CV. So the shorthand notation for this control volume is CV and the shorthand notation for this is CM. Okay, so allows us to rate of change of some quantity in CV to that with the rate of change of quantity in CM. Okay, so let's now derive Reynolds transport theorem. Okay, now let's say at t is equal to t naught, my control mass looks like this. So my control mass, let's say it looks like this. Okay, and I am defining the control volume in such a way that the control volume overlaps this control mass. So let's just draw it with red color. So I'm defining my control volume in such a way that it overlaps the control mass at t equal to t naught. Okay, all right. So this is my control mass and this is my control volume. Okay, now let's say because of the fluid flow, the control, since the infinitesimal volume elements would flow, that's why this can change its shape and structure. So let's say at t is equal to t naught plus delta t, my control mass, it becomes, so the control volume would remain as it is. Okay, and the control mass, let's say it gets deformed and looks something like this. Okay, all right. Now please note that the control mass and control volume is a 3D shaped boundary, and I've just drawn them in 2D. So don't think that this is a 2D boundary, this is actually a 3D boundary. Okay, so let's say in 2D, let's say if it would look like a circle, in 3D it is actually a sphere. Okay, the boundary is actually the spherical boundary. Okay, got it? Now let's mark these regions as region 1, region 2 and region 3. Let's not write it here. Let's mark this as this whole region. So what one would correspond to? One would correspond to region with this volume. Okay, and let's mark this as 2. Similarly, 2 would correspond to this volume. Okay, and let's mark this as 3. 3 would correspond to this volume. Okay, next let's define eta as amount of extensive property, some property which depends upon the size of the system that you have taken divided by the mass of system. Okay, so let's say I am considering the extensive property mass, then this eta for the extensive property mass would be mass by mass, that would be 1. Similarly, let's say if I am considering extensive property as linear momentum, so that would be mass times velocity divided by mass. Mass can cancel out with mass, and eta for extensive property linear momentum would become nothing but velocity. Okay, for if I consider extensive property as linear momentum, this is equal to 1 for mass taken as an extensive property. Okay, all right. So let's denote this amount of extensive property as n. Okay, so now let's say I have this boundary and I am considering a differential mass dm. Okay, then what can I say about the amount of extensive property given eta? So that would be nothing but integration eta dm, right? Okay, integrated over volume V. So from now onwards I'll write volume as denoted like this, so that there is no confusion between velocity and volume. Okay, so this would denote velocity and this would denote volume. Alright, so this is integrated over the volume. So whatever the volume for which I am defining this volume, this elemental mass dm, integrated over that volume would give me the total extensive property in that volume V. Okay, so let me repeat what we have done so far. So we want to derive the Reynolds transport theorem. For that we considered a control mass and control volume, and we drew control volume in such a way that it overlaps the control mass. So let's say this is how the control mass and the control volume at time t equal to t naught. Okay, now at t equal to t naught plus delta t, so in time delta t, let's say the control mass shifts a bit. Okay, it deforms a bit in time t delta t and looks something like this. Okay, so please note that this is actually two different images. Let's say I have taken the photograph at t equal to t naught in with respect to same origin. So let's say this is my origin, and I have taken another image like this, and this is my origin. So don't get confused that so let at t equal to t naught and this looks like that, at t equal to t naught plus delta t this looks like that. So it might be the case that this control volume has gone from here till here, and similarly the control mass has gone from here to here. Okay, so don't get confused with that. It is actually not moved. These are two different photographs with same origin. Okay, so let's just remove this. This is not required. Now we are interested in finding the rate of change of this extensive property n. Okay, so this n corresponds to system. So what is the rate of change of quantity for the system? This is what we are interested in finding. So this, using the simple, from our knowledge we can write the derivative as limit delta t approaches to 0, n of system t equal to t naught plus delta t minus n of system at t is equal to t naught divided by delta t. Okay, well, let's write it in more conventional manner. This would be t is equal to t naught plus delta t. This is t is equal to t naught divided by delta t. Okay, so before deriving further, I think I should tell you more about the sense system. So let's say if my control volume is like this. Okay, so control volume is simply an imaginary boundary, right? So let's say there is no fluid inside this control volume. Let's say there is nothing inside this control volume. This is completely empty. This is a boundary but does not contain anything. So what can I say about n system? Obviously, if this is empty, n system will be 0, because let's say the mass of my system, so system is the fluid particles or infinitesimal fluid elements. So the mass, so there is nothing inside this fluid, this imaginary boundary control volume. So I should also at this point tell you that the boundary of this control volume is called control surface, which has the shorthand notation CS, and the volume enclosed, so this hole with the volume is called control volume, and the surface is called the control surface. Okay, so if this control surface does not bound any fluid particle or any fluid, then n system would be obviously be 0. Okay, and let's say this is my control mass. Now since control mass always encloses the particles, right? So it can never be 0. N system cannot be 0 inside your control volume, control mass. So this is your control mass, this is your control volume. Okay, now let's say this control mass contains some quantity of n system. Okay, and let's say I have drawn the control volume like this. Okay, so in that case, what will be the n system inside my control volume? So this is my control volume. So what would be n system inside my control volume? It would be simply n system by 2, right? Okay, I hope now that the understanding of control system and control mass and n system inside the control mass and control volume is clear to you. Okay, all right, now let's come to this problem. So we want to find dn system by dt, which we can also write it as limit delta t approaches to 0, and system at t equal to t naught plus delta t minus n system at t equal to t naught divided by delta t. Okay, now what can I say about n system at t is equal to t naught plus delta t? As I mentioned, n system at t equal to t naught plus delta t would be inside this control mass, right? So can I just write n system, let's just write it here. So can I just write n system at t is equal to t naught plus delta t as n system in region 2 plus n system in region 3? Okay, because n system 2 plus n system 3 corresponds to your control mass, right? So that's why n system at t equal to t naught plus delta t can be written by this, can be written using n system in region 2 plus n system in region 3. Okay, now since we are interested in writing this right hand side in terms of my control volume, the quantity inside my control volume, I would like now to replace one of these quantities with n system in my CV. Okay, now what is n system in my n system in CV? What would be that? That would be nothing but n system in region 1 plus n system in region 2, right? Okay, I hope this is clear, that why n system CV is equal to n system 1 plus n system 2, because since this is my control volume, okay, so what is the quantity that would be enclosed, that would be contained inside this control volume? That quantity will be the quantity in region 1 plus the quantity in region 2, right? Okay, and that's what we have written here, that n system in CV is quantity in system 1 and quantity in system 2. Okay, okay. So let's replace, since now 2 can be written in terms of n system in CV, so we'll have n system in region 2 can be written as n system in CV minus n system in region 1. We'll use this to replace, so this with this, so we can write n system CV minus n system in region 1 plus n system in region 3. Okay, so this is my n system at t equal to t naught plus delta t given by n system in CV, n system in region 1 and n system in region 3. Okay, now let's use this n system at t equal to t naught plus delta t in this expression. Okay, so we'll have dn system by dt equal to limit delta t approaches to 0 and system t plus t equal to t naught plus delta t, this will be written with this expression. Okay, so this will become n system. So let me now just drop this subscripts n system. Okay, so dropping subscript system, I can write this as n CV minus n, or let's just write it as n CV minus n in region 1 plus n in region 3 minus n at t is equal to t naught divided by delta t. Okay, okay. Now what is n at t equal to t naught? So at t equal to t naught we had this, and at t equal to t naught would be this. Now can you just see what is n at t equal to t naught? This is nothing but NCV at t equal to t naught. Okay, so now this might get confused, so there can be NCV at t is equal to t naught, there can be NCV at t is equal to t naught plus delta t. So let's write the time values also with these subscripts. So NCV, this was at t is equal to t naught, t equal to t naught plus delta t. This n1 was with t naught plus delta at t equal to t naught plus delta t. N3 was also at t equal to t naught plus delta t, and n at t equal to t naught is NCV at t equal to t naught. Okay, all right. So now let's just, so we can see here that here we have NCV t naught plus delta t minus NCV t naught divided by delta t. Okay, so we can just write this as limit delta t approaches to 0 ncv t naught plus delta t minus ncv at t naught divided by delta t. So I have written this, I have written this term, I have written this term. Now let's write the other two terms. The other two terms are minus n in region 1 t naught plus delta t divided by delta t plus n in region 3 t naught plus delta t divided by delta t. Okay. Now what is this term? This is nothing but d ncv by dt, or instead let's just write that this is 1, this is 2 and this is 3. So let's evaluate 1 first. So 1 is limit del t approaches to 0 ncv t naught plus del t minus ncv t naught divided by del t, and this is nothing but dn cv by dt. And since n is equal to integration of eta dm, and dm also we can over some volume v, and dm we can also write, knowing the density of the fluid, we can write this as rho times d volume over volume v, and cv would become over the control volume cv eta rho dv. Okay, so let's write d and cv here. So this would become d by dt integral eta rho dv over control volume cv. Okay, so we got 1 equal to d by dt integral of cv eta rho dv. Okay, all right. Now to evaluate terms 2 and 3, let's first understand a quick problem. So let's say if I have given you a surface, a 3D surface like this. Okay, let's say I have given you a 3D surface like this, and let's say the fluid flow is, let's say the fluid flow is like this. Okay, all right. Now let's consider an elemental surface dA on this surface, on this given surface. Okay, and let's say the dA vector of the surface is pointing, I'm just exaggerating this dA vector for clarity. So let's say dA vector is like this. Now because of the flow field, or because of the fluid flow, what can you say about, let's say the molecules or the fluid elements which were present here? What can you say about them in later time t naught plus delta t? So can I say that in time t naught plus delta t, they must have moved like this? Correct? Okay, so this was your v vector. This was your v vector. Okay, I have just exaggerated it for the clarity, but let me just concentrate on this green portion again. So this was my elemental surface area at time t naught plus delta t at time t naught, and this is how the particles must have moved in time t naught plus delta t. This is my dA vector and this is my velocity vector, correct? Now if I ask you the question, what is this volume? So let's say this is the figure. So what is the volume of this portion? The answer is, this volume is V dot dA delta t. Okay, so this would be the volume of this portion. All right, now if this problem is clear to you, let's now concentrate on our original problem. So what we had was, let's again just copy paste this image. Okay, we had this problem. Now if you can see, the same thing is happening over here. So if your velocity field, if your velocity flow field is like this, and again if I consider an elemental area like this, let's say like this, and I ask you what would be this volume, your answer would be, so this small volume dV would be simply V dot dA delta t, V dot dA delta t. Okay, where dA is the elemental area vector on this surface, on this surface. Okay, correct? All right, now if I ask you what is n3, n3 was integral over this volume 3. Okay, integral over this region 3 eta rho dV, correct? Now let's say this volume element is this dV, so can I just write this dV as integral eta rho over region 3 V dot dA delta t, right? Okay, now since this delta t would be independent of the region, the volume element that you have chosen, so I can take it outside. So this would become this thing, and if I see over here, I have a term limit del t approaches to 0 and 3 at t naught plus delta t divided by delta t. So what would 3 become? So 3 was n3 at t naught plus delta t divided by delta t with limit delta t approaches to 0. So this is, so we are writing this n3 in this, okay, to get delta t integration eta rho v dot dA over region 3 divided by delta t. This delta t would cancel out with delta t and will be left with this expression. With now this surface is actually this surface, so let's call it CS3. Okay, so this is CS3. okay, so the integral of this dA vector is over CS3. okay, similarly if I write 1, if I write 2, this 2 is will take the negative sign. Let's not take negative sign in this 2, so then this 2 will become, and this 2 is, so 2 is n1 t naught plus delta t limit delta t approaches to 0 divided by delta t. So with similar arguments we will get this as CS1 eta rho v dot dA. okay, now if you think carefully, we have done one mistake in this derivation. And what is that small mistake? So the mistake is of this sign convention actually. Okay, so now if you see from the start of this problem, we have considered that this 3 has let's say the particles in 3 have moved from my control mass, have moved from this control volume outside. Okay, so the particles in 3 have exited this control volume, right? So this red one was our control volume, and we assumed that this part has moved outside of this control volume, right? Or in other words, dn3, or I have written it like this, dn3 is a differential extensive property that has come outside of this control volume, right? And similarly dn1 from this image, we have assumed that dn1 is the differential extensive property that has entered control volume. Okay, so we have assumed from the beginning of this problem that dn3 is the differential extensive property that has exited CV in time delta t. dn3 is the amount of differential extensive property that has exited CV, and dn1 is the amount of differential extensive property that has entered CV. Okay, and when we are getting these expressions, we are saying that we'll calculate v vector dot dA vector to get, so the sign of v dot dA should tell me whether the dn or the differential of this extensive property has entered. So ideally it should tell me that whether this dn has entered or exited my control volume. Okay, but I have already assumed what is entering and what is exiting, right? So since we should do analysis in general, okay, which we have not taken in this case, so in general we should assume signs to be positive, and if the real sign of that thing is negative, while doing the calculations you eventually would get the sign negative. Alright, but since we have assumed n1 that it would be a negative quantity, and we are saying this would give me a negative quantity, so to correct that thing, what we should do currently, we should put a negative sign over here. Okay, so this negative sign is there because in the beginning we have assumed that this dn1 has entered my system and dn3 has exited my system, and from this dot product we are saying that we will get anyway we will get whether the quantity is exiting or entering my system, my control volume. Okay, so I hope this why I have put negative sign over here is clear to you. Okay, in short, if your v dot dA comes out to be positive, then let's say comes out to be positive for that control surface, then the quantity must be exiting from that control surface, and if v dot dA is negative, then the quantity must be entering the control surface. Okay, or let's say if you don't want to put this negative sign, then what is the other alternative that we have? The other alternative would have been this. That is, let's say you are given a problem and you know that, so let's assume a problem. Let's consider a problem. This is your, let's say, pipe. Okay, all right, and let's say I define my control volume like this. Okay, and let's say the fluid is actually flowing like this inside this pipe. So let's say the fluid is, let's say, flowing like this. Okay, now I know beforehand that on this surface the fluid is entering, and on this surface fluid is exiting. Okay, so then instead of finding v dot dA vector, I will put a negative sign and measure the quantity for the one in which this quantity is entering, and put a positive sign for the one in which the fluid is exiting. Okay, and find the mode value of this thing. So let's not follow this convention for putting the magnitude. Okay, let's just follow this convention that we'll put a negative sign, and now if your v dot dA is greater than 0, we'll say that the quantity must be exiting from the control surface, and if this v dot dA is less than 0, the quantity must be entering the control surface. Okay, alright. So now what would dn system upon dt become? So now we have 1, we have 2, and we have 3. So let's write dn system by dt. So first of all we have 1 is given by dnc, 1 is given by this expression, d by dt integral cv, d by dt integral cv and eta rho dv. Okay, and this v should be like this now. Okay, then we have 2 is given by this and 3 is given by this. So just put it. So this will be minus integral cs1 eta rho b dot dA plus cs3 eta rho b dot dA. Okay, now so there is a negative sign here which you have to also consider. So that's why with 2 another negative sign would come and this would become plus. Okay, now if I ask you what is cs1 and what is cs3, so let's again copy paste this image. Okay, so what is cs3? cs3 is this surface. Okay, cs3 is this surface. And what is cs1? cs1 is this surface. Correct? So now what would be cs1 plus cs3? That would be nothing but the control surface, which is this. Let me just draw it with some other color. My control surface now would be this would be my cs1 plus cs3. Okay, so I can just write cs1 plus cs3 as cs. Okay, so I can just write these two terms as one term, and that will be, let me just write this first. dn system, d by dt of n system would be d by dt integral eta rho dv control volume plus integral over now the control surface eta rho v dot dA. Okay, so this is referred to as Reynolds transport theorem. Okay, so it relates your extensive quantity in control mass with extensive quantity in control volume, because this is this is the volume of the control, this is the volume of your control volume, and this is the boundary of your control volume, right? Or the surface of your control volume, right? Okay, so this term is rate of change of system extensive property, and this term is the rate of change of amount of property n in control volume, and this term is the rate at which property n is exiting the surface of control volume. Okay, where eta is the total extensive quantity and divided by the mass m, and v vector is the velocity of fluid. Okay, and this velocity of fluid is with respect to the control volume. So why I have used with respect to control volume? Let's understand this. So let's say you have a cube, okay, and there is this free jet impinging on this cube. Okay, now because of this free jet, let's say we are given the situation that this is moving with velocity, let's say u vector, with a constant velocity u vector. Okay, and let's say you are given a question with some known things. You are given a question that what would be this u vector. So what would be this u vector, or let's say you are given a question what is the force that this jet would apply on this cube given it is moving with constant velocity u vector. Okay, so now to approach such problems, since our system of interest is this cube and not the jet, we'll take the control volume like this, and that control volume is also moving with this cube at a velocity u vector. Now let's say in my lab frame this is velocity v vector, and if you want to apply now Reynolds transport theorem on this problem, you have to take the velocity of this coming fluid. So in Reynolds transport theorem, velocity, let's say just v vector. Okay, so since this v vector is getting confused with this v vector, let's just write it as x y z. Okay, so this x y z corresponds to the coordinate system in control volume CV. Okay, so in RTT, v vector x y z is actually the velocity of fluid with respect to control volume CV, or in this case this v vector x y z will be equal to the velocity of fluid with respect to ground minus the velocity of control volume with respect to ground. So what is the velocity of this fluid with respect to ground? That is v vector. And what is the velocity of control volume with respect to ground? That is u vector. So in this case, my vxyz that I will plug in, or let's just write it over here itself. This is xyz. So this means that this is the xyz means, okay, it's becoming untidy, so let's just write it again. So this is v vector xyz. Okay, so where this vxyz is the velocity of the fluid with respect to control volume, and for problems like this we have to first find the velocity of the fluid with respect to the control volume, and that velocity will plug in this expression. Okay, all right, this will be more clear that this vxyz, the relative velocity of fluid with respect to control volume, how should we take it? This would become more clear when we'll do some problems on this Reynolds transport theorem. So remember when I said that we'll use Reynolds transport theorem for this case. So we had a plate and we are holding the plate with some velocity, with some force Rx. There is some free jet which is going like this, and we have to find Rx. So we'll do one problem like this, then we'll do also some other problems where this concept of Vx will become more clear. Okay.